Happy to see you again in Operating System Concepts. Continuing our topic on operating system concept, today we are going to look how OS actually manages the disk and also I/O that is coming to the system. This is also part of the resources being used by the process. So among the topics that we are going to look at today is the categories, the DMA, I/O facilities and design, buffering, the scheduling of input-output, and also the introduction of disk cache and RAID. So for the first part, we are going to look at the categories of I/O devices and the techniques being used in managing I/O. Basically, I/O devices are the peripherals that you use between you and your computer to communicate and interact. For example, you use your mouse and keyboards to send whatever request that you want to the computer. For example, you use your keyboard to enter the commands, and also you use your mouse to point to the app icon that you want to actually start. While at the same time, the output device is perhaps the printer or the monitor. The monitor is being used to actually show you what is being processed, and also the printer is sending to you whatever you have printed out or want to have a report on. And based on that, we have a couple of categories of I/O devices. First of all is the human readable devices, which is for communicating with the computer user. These are the things that we actually understand. For example, the printers, the terminals, the video display, the keyboard, and also mouse. And for the machine readable, this is really for the computer to understand something. For example, the disk drives, the USB keys, sensors, and controllers. For example, without the disk drive, the computer will not actually understand whatever devices you are actually plugging into the hardware. And then lastly is for communication. So this is basically suitable for communicating with remote devices. Means that you use this to actually communicate with other machine, okay, aside from your own devices. So for example, you have modems, you have line drivers, and also the network interface card to communicate with the network or from people from afar. So these are the three categories of I/O devices: the human readable, machine readable, and communication device. And apart from those categories, we differentiate I/O devices in terms of this information. So you can see sometimes we differentiate I/O devices based on, first of all, their data rate, means how fast does the device can actually transfer the data. For example, between the click of the mouse to the response that a computer actually read it. And also the response times between the keyboard or the key that you press with the response time of the computer. If you notice, this is usually very important if you are actually using gaming devices. For example, you want fast response time between the use of your keyboard and your mouse so that you can actually interact faster with whatever you see on the screen. Secondly, is the application being used by the devices, or what application will use the device. For example, you use a monitor, so sometimes it is the difference between a gaming monitor and perhaps for just an office use monitor. So this is also one of the consideration when choosing a device. Secondly and thirdly is the complexity of control. What is being controlled and how is it done? Sometimes the devices just accept user touch, for example, and sometimes, for example, the camera can detect your movement. So how fast is the response between the read of your face, for example, to the identification of the system to whatever it reads on the camera. The fourth is the unit of transfer. You have the data rate previously. Now what is the unit of transfer? Is it the frame per second? Is it data per second, for example? And then we have data representation. Is it in terms of block, stream, or in terms of movement? Does the device actually detect movement? Does it detect actually the magnetic polarity of whatever the user is on, for example? Is it actually sending data? Is it actually send a stream of video? So that is also one of the difference between the devices that you want to buy. And then lastly is how does the device actually handles error condition. Can it actually detect if, let's say, there is error in the reading of the data or in the reading of whatever you are transmitting. So this is also one of the things, is the data and the device actually can handle the error condition that could cause from the user or perhaps during data transfer. So these are the differences in terms of usually in choosing the IO devices with relevant tasks and perhaps with the user's budget or requirement. So in terms of method to perform I/O, there are two distinct methods to perform the input and output. First of all is the program I/O, whereby the processor issues an I/O command on behalf of a processor to an I/O module. For example, let's say you are printing from a Word application. So when you click on the print icon, basically that process is requesting for the use of the printer, which is an I/O devices. And then also there are interrupt-driven I/O, means that sometimes processors need to send out messages in order for it to be noticed. For example, after an input has been keyed in by the user, so it wants to send a response. So this is one way of interrupt-driven I/O, and usually sometimes after, for example, doing certain tasks, you need to send certain signals for either to the system or to the user in terms of using certain devices or requesting certain data. So there are interrupt-driven I/O in this case, whereby the processor issues an I/O command still on behalf of the process. Means that, for example, after the task of getting the input from the user, the process itself wants to send out whether the data being sent or keyed in by the user is actually the correct data. And let's say after the printer has finished processing, they want a certain detection how that print process is actually finished. So perhaps after the printer process has finished printing, then it will send on the screen the printer has successfully finished printing the document. So in this case, if non-blocking means that the processor continues to execute instruction of the process that issued the I/O command, and if blocking, it will actually wait for a certain condition to happen. Means that until, for example, the user actually clicks on the OK button on the screen, then it will not continue to the next instruction. Alright, and also in this case, you will actually know in the next part is the use of the DMA, which is controlling the exchange rate between the main memory and the I/O module. Why is it needed? Because sometimes when we're actually printing something, okay, for example, when you print a document, that data is being sent into the main memory and that data is being printed to the I/O devices, which is, for example, in this case, the printer. So whatever data that needs to be transferred will need to be stored in the main memory before it can be output into the printer. So you will get to know the use of the DMA later on. So what is actually the DMA, or the direct memory access? Now, in order to understand the benefit of having a DMA, is you need to understand first that whatever task that is handled on the system, you usually have to have the processor chipping in on actually finding out whatever task need to be done, or in terms of swapping, or in terms of having the dispatcher, for example. So you need to have the CPU or the processor always monitoring between one process until another. So we have the DMA in this case because we want for the process and the I/O device to actually have constant direct access. It means that without the micromanagement from the processor, which is instructed by the OS, now process and I/O can actually do and send data directly. Means that the processor here does not need to be constantly monitoring the progress of the data transfer. So by having DMA, it allows the data to be sent directly from any attached peripheral or I/O devices to the memory of the computer motherboard. So let's say when you want to print a document, okay, once you hit print, the CPU will not need to monitor what is the current line that you are actually printing. So once the printer process is activated, the CPU can leave the process, do other tasks, and then only comes back when the whole print process is done. So here the processor is freed from involvement of the data transfer, thus speeding up the overall computer operation because the CPU can do other things, which is execution of other processes instead of having to monitor the progress of the I/O data transfer. Next, we are going to look at the I/O facilities design. So in terms of having a proper facilities design for the I/O, there are two objectives. First is the efficiency. Efficiency means that whenever you are actually doing input and output, you want to actually make sure that the transfer went smoothly and there are no delays in sending the data and also towards the required devices. So this is the major effort in I/O device because we don't want to actually waste the CPU time in waiting for the data to be transferred and delivered to the user. So usually the causes of bottleneck is the I/O transfer is slow compared to the speed of the CPU. And then how can the data transfer be improved? So nowadays we have very high speed, for example SSD, compared to the previous normal hard disk that we have. So this is also one of the effort to increase the efficiency in data transfer and also the speed of the processing of modern computers. Next, in terms of generality, because we actually nowadays we don't require the disk installation because all of these are done in the background. We want for our system to instantly recognize a device each time we just plug in the device. So once you plug in your camera, for example, it instantly recognizes that is a video camera. When you plug in a microphone, it instantly recognizes there is a microphone for recording sounds. When you actually plugging in your gamepad, for example, your mouse, your keyboard, it instantly recognizes what device that is, what is it being used for, what is the data transfer, what is the data being transferred. So this is also the main aim of the facility design for the I/O devices in terms of generality. So whatever device you plug in, it instantly recognizes what the device is and what is it used for. And apart from that, of course, sometimes we don't have the necessary drivers. So it's just enough if we have the basic functionality of the device. And then later on, when you use the device, perhaps you can download the required or proper files for running the device. So these two objectives in terms of efficiency and generality is the main aim of I/O facility design. It means that it brings you the capability of the I/O and the use of the I/O efficiently and having a general use for that device. So in terms of managing the interface between the I/O and the user, we need to understand the representation model that is depicted here. So in this model, we see the relationship between the user, the system, and the hardware. If you remember, in our earliest chapter of OS concept, we have established that the role of the operating system is to be an intermediate party that helps the user in order to use the hardware. So in this sense, we have the following layers in order to help the user to communicate or use the hardware. So from the user to the system and to the hardware, we have these layers of system involved in order to get the user wants what they want with the hardware. So we have the logical I/O, device I/O, the scheduling and control, followed by the directory management, file system, and the physical organization. So basically the logical I/O is the representation of how the humans see the structure of the hardware and whatever we have inside the system. For example, imagine you are opening the File Explorer or the control panel when you want to add a new hardware. Whatever hardware that you have or devices that is connected to your system is represented in a sort of directory. So this is a logical representation of what I/O devices that we have inside the system, and the OS helps manages those I/O devices. So if let's say you want to add a new device and whether we have a new driver for those device, the OS will always help us to update or perhaps find the suitable driver for those I/O devices. Secondly is the device I/O. So basically, just like we have input and output to the monitor, for example, so any other devices have their own input and output. So we must recognize, or the system itself must be able to recognize whenever we plug in a device, which type of data can be accepted as the input for the device and what type of data must or can be outputted by that particular device. For example, a printer will receive whatever digital data in terms of Word document, and it will output a printed file from the printer when we want it. That is just one example. And then also we have the scheduling and control. Just like any other resources, I/O is also part of the resources that is being shared by the user and also the process. So when we are talking about resources, of course, they need proper scheduling and control. This again is the role of the operating system to decide when or where does the device can be connected to a needed process. And then also the directory management and the file system. It means that just like the logical representation before, all the files and all the data that needs to be submitted to the I/O devices must have a proper structure so that those data can safely be transmitted to the needed I/O devices. And then, of course, lastly is the actual physical organization. So each of these devices have their own addresses so that the OS can easily find them in the selected or this designated port. So it's just not enough that the user just want to use the hardware. In the middle, we have the operating system that is doing all those management for us. The next part is on buffering. So why is buffering needed? If you notice, between communication or the transfer of data between one process to the actual hardware, we need to actually send a couple bytes of data. So just imagine the transfer, if it's doing directly and without any buffer, then there must be a certain delay between the transmission of the file from the hard disk to the ability of the hardware to receive the data. Remember that the transmission or the transfer rate between the hard disk and the I/O devices is usually different. And sometimes this difference will cause certain delay. So this is why we need the facility of a buffer. So buffer is basically a temporary place where data can be accumulated while it is being transmitted to the targeted I/O devices. So for this part, we are going to look at how is buffering done and how does buffering help the transmission of data between processes and the I/O device. So just like I've said earlier, the option of having buffer is to help the performance of data transfer between the process or even between I/O devices themselves. And usually, by having a buffer, input transfer are done in advance before an actual request is being made. Usually, there is an estimation. For example, let's say you are watching a video, so the system will actually estimate that you will try to watch the whole video. So while you are watching the first frame or the first 10 seconds of a video, the portion of the remaining video will be loaded into a buffer. So this data transfer is being done as you are watching the video. So the remaining of that particular movie, okay, will be loaded into a buffer, and it will be unloaded as you watch the video slowly until the end. So this using of buffer will actually help you didn't notice the transfer rate that perhaps is lagging between the movie side and also the actual process inside your computer. That's why if let's say the transfer rate is very low, sometimes you will see the disturbance in the transfer of the movie themselves, and the movie that you watch will have a certain lag in transmission. So this is where buffering helps the data transfer when the process wants to use the data. You have some sort of a placement or a placeholder where you can hold the data in between the transfer so that you do not have to transfer directly between the source and the destination. Why? Because like I said earlier, it's because sometimes the rate of transfer between your device or your hard disk is not the same as the capability of the transfer rate of the I/O devices. Sometimes or most of the time, the I/O device themselves have certain limitation compared to your hard disk, for example. Even so, nowadays we have SSD. So just imagine if you have a fast SSD, but at the same time, your for example, CD or disk drive or even DVD or Blu-ray does not have the capability to transfer those data very fast. So you need the help as the buffer of the buffer to be an intermediary party to hold the data before it is transmitted to the actual location. This is the purpose of the buffer. So this first condition, which is no buffering, is you have a potential of a deadlock. Because just imagine if let's say the I/O device transmit data very slow compared to the capability of your SSD, which contain your process or even your RAM. Usually RAM, the data transfer is very fast compared to the transfer rate from your I/O device. So for example, you are plugging in your thumb drive, and while the thumb drive is being written, you need to wait for all the data from the thumb drive to be loaded into your RAM, for example. So this, while waiting, there will be a potential that not to happen, because sometimes, let's say, because the transfer rate is too low, there will be a potential for a process to become unresponsive because it needs to wait for all the data to be loaded. So this is the danger when you have no buffer, because you need to transfer directly between the I/O device towards the user process. In the second example, we have a single buffering mode of transmission. So compared to the previous setting, now you have the buffer in the middle. So in between the transmission of the I/O device to the user process, you have a temporary buffer to hold all the data as being loaded. And as it's being loaded, it is transmitted to the user, and the user process can immediately use those data according to the user instruction. Okay, compared to no buffering method where you need to have all the data loaded before you can use it, a buffering system enables for the data to be used as it is being transmitted. So this simplest form support the operating system that can provide a very much more faster and more efficient processing, because you do not have to wait for all the data to be loaded before it can be used. So you have somewhere you can place the data, and the data can be used as the loading is being done. And of course, as technology matures, you have now a double buffer where you can hold much more than one buffer of data. So this is very important if you need to change between one buffer size into another. And in this case, the buffer size can also be increased because now you have more than one buffer. So of course, in terms of performance, it performs much better than a single buffer system. And of course, if we did a much more faster processing between the I/O device and the user process, the circular buffer is introduced. Basically, a circular buffer is where we have more than one and also more than two buffers at the same time. This is needed when an operation must keep up with the user process. So let's say whatever data that is being transmitted, okay, is being used by the process. This is usually true if you are actually going to do image processing, for example, where you need to actually process live data and that data is being streamed and at the same time being analyzed by the process. So in this case, you need much more buffer than ordinary that you need. Let's say previously you just need one or two buffer perhaps just to collect a user that is typing on a keyboard, for example. But if let's say the I/O transmit very resource intensive, such as the using of image processing, then you need much more than two buffers for this type of process. So this is where a circular buffer system is needed, because you need a much more faster update from the I/O device. Hence, the data transfer rate must be much more faster and the buffer size must be able to store as many live information as much as it can as the process is processing it. Before we continue to the next part, which is on I/O scheduling and disk performance, let's take a 5-minute break and recap of what we have learned so far. So you look at the buffering system, the characteristic of I/O management. So try and actually understand why it's done that way and why buffering is needed. Okay, so take a 5-minute break before we continue to part 5 on I/O scheduling. So for this part, we are going to look at what happens internally when a request comes for a certain sector in your hard disk. So as you know, in your hard disk, we have this sort of cylinder. Alright, so this example is just an old hard disk that I have in spare. Okay, just for you to imagine what happens in your hard disk when a request for a data in your hard disk happens. So in your hard disk, we have this type of structure. So for example, you have the spindle with the disk is spinning, and you have the track and the sector. And in your hard disk, you have the read and write head. So once you are actually transferring data either for reading a data or writing, which is saving a data onto your hard disk, it needs to actually search for a specific track and a sector before the reading can actually be done. So for this part, we are going to look at how much time will be spent for the track before it's being found and actual read and write can be done. So for the first method, we are going to look at the first in and first out seek method. So for example, in this scenario, we have the request for this track number. So these number are the track number. So we have track 55, 58, 39, 18, 90, 160, 150, 38, and 184. So these are the requests that comes, which signify to the system, please look for this track because there are certain data there. Okay, so the request is done in a sequential order. It is fair to all process because it comes based on the request that comes in. So whatever request that comes in, it will treat that request first. So if the request comes for 55 first, okay, we will search for track number 55 first, and then followed by the second request, third request, and so on. So this is viewed as a very fair process. So it approximates random scheduling in performance, and if there are many processes competing for the disk, it will just do whatever that came first and then process accordingly to the request number. So this is how the graph will look like. It is based on, first of all, okay, let's say the current track position is on track 100. So the next request will be for track 55. So it will go to track 55, followed by track 58, okay, and then track 39, track 18, 90, and so on. So for this type of question, you just need to draw the graph and show how does the tracking distance, or how does the tracking location changes according to the request. Now, the second method of seek is for the shortest service time first. So compared to the previous one, this one actually try to analyze which request is actually nearest to the previous location. Okay, so for example, still the same request, 55, 58, 39, 18, 90, 160, 150, 38, and 184. Okay, now we are not doing first in, first out. Instead, we are doing shortest service time first. Okay, so the key here is to look for the nearest of the track with the current position. So let's say, just like before, the current track is track 100, so it's located here. Then in between, okay, this is the track request previously. So we have track 90 and 150 in between track 100. So which of these is the nearest to track number 100? Okay, so based on the proximity of the location, now we will choose 90. Okay, so after it arrives at track 90, now we need to calculate between track 90 and track 58, or track 90 and track 150. Which one is actually the closest? So of course, after you count it, the closest is track 58. Okay, so the next location, it will move to the track 58. And after that, it will still to need to calculate again between track 58 and the outstanding track 150, or between track 58 and track 55. So which one is the closest? Again, based on the calculation, of course, this time the closest is track 55. And then, of course, 150 is still the longest there on the track. And then next one, 55 compared to 39 and 150. Of course, 39 is the closest. And then 39, 150, and 39, 38. Of course, 38 will be chosen. And then 38 and 18, or 38 and 150. Again, 18 will be chosen. So after it arrives at the end of the track, now it will go to the outstanding track that is not serviced yet. So of course, it will now go to 150, and then 150 will go to 160, 160 will go to 184. So this how shortest service time first works. It will look for the closest range from the previous track location. So in this case, it will move downward because that is the most closest proximity before it actually go back to the outstanding track that is not serviced yet. Okay, the key here, it will always choose the minimum seek time. Now, the second method is also known as the elevator algorithm. Okay, the former name is the scan method, where it moves in one direction before it goes to the opposite direction next. So how does an elevator algorithm work? Remember how does an elevator work? It actually go to the furthest location first, or the lowest location first, depending on which button you are pressing. Okay, so in the scan method, I will illustrate in this example. So still the same request, 55, 58, 39, 18, 90, 160, 150, 38, and 184. Now, remember the current track location is on track 100. So from this location, it will move to the outstanding or the larger number first. So from 100, it will go to 150, 160, and 184. Until all the tracks are finished, then it will go down to seek for any outstanding track seeking in the opposite direction. So after this, it will go to 90, 58, 55, 39, 38, and 18. So this is how scan seeking works. It goes to one direction before it returns to the opposite direction to seek the outstanding track request. The last seeking method is the C-scan. Now, in contrast to the scan method, C-scan actually moves in one direction only. So let's say the seeking already moved to the left side of the track, it will move that continuously until all track request has been finished. Or if it's moved to the left, then it will finish that request until all request number are finished. So in this example, still we are looking at the same track number request 55, 58, 39, 18, 90, 160, 150, 38, 184. So again, the current track location is on track 100. So it will move to location 150, 160, 184. Now compared to the previously, now it will go to straight to track 18, 38, 39, 55, 58, and 90. So it moves in one direction only. Okay, compared to the scan, it will move to the end of the track, then go back. Now C-scan move in one circular direction only. So how do you do the graph? Based on the axis of the track. So basically, that's it for how track seeking is being done in terms of hard disk track seeking. You have the C-scan, scan, okay, shorter service time, and you have the first in, first out. For this part, we are going to look at virtual memory. If you remember, active processes will come in and blocked or suspended process will be swapped out from the main memory. So in this part, we are going to look at some of the placement method being used when processes needs to actually be swapped out or swapped in into the main memory. Basically, for a placement policy, it determines where in the real memory does a process space needs to go. And also when process is not active or being suspended, where is it going out later. So this determines when or where does a process needs to go in after it's being swapped out, and what determines the characteristic of those process that needs to go in or out of a certain placement in the memory. What we need to know about the replacement policy is that it deals with the selection of the process page that need to go in, and perhaps after a while need to go out, and perhaps if it still have a cycle, it needs to be brought in again. So this policy determines which process page actually needs to go out after a while, or perhaps after that needs to come in again to do its remaining process. The optimal method, the least usually used, and also the first in, first out are some of the algorithms being used for the page selection process. So we will look at it one by one, and I will explain you to do how does the selection work. For optimal policy, we are going to look at the policy which select the page for which the time to the next reference is the longest. And this needs that the OS always know the row or the order of the process that will be coming in advance, so that it can do the proper selection for which process will actually go into the available slot. So for example, we have this order of process that will be coming in. We have 2, 3, 2, 1, 5, 2, 4, 5, 3, 2, 5, and 2. Okay, and then we have 3 frames of memory that can be allocated to those process. Now, for the first order, we see that, okay, there is available slot, so 2 can come in here. Next one, we have still available slot and 3 coming in, so 3 can use this frame. So next one, process 2 again has the order to actually do some instruction. So because 2 is already here in the available frame, so 2 is just using the available slot there. Now next, 1 comes in, so 1 will use the previously available slot, which is under 3. Now let's say after this cycle, okay, 1 actually finishes, okay, and 5 comes in. So 5 will actually be allocated to the previous location that 1 was previously in, right? So in this case, every time a new process comes in, a new page fault will be generated. So in this case, okay, there is 1 page fault, okay, 5 is coming in and using the previously slot allocated to 1. And then process 2 proceed again. So because process 2 is already created, so nothing changes, right? So next one, process 4 comes in. So now we need to make a decision which process actually needs to go out. Okay, previously we have process 2, 3, and 5. Now process 4 is coming in. So what or how to decide which process needs to go out? So we need to see here. Alright, so for process 3, okay, there will be 3 cycle until 2 is activated again. If you see here, okay, from here, the location is 1, 2, 3, and then only will 2 need to do the instruction again. Okay, remember OS have all the information regarding the process that is going to execute or not. And then for process 3, it will be in another 2 cycle. So 1, 2, 3 will come. And then for process 5, it will come again for 1 cycle here. So based on this cycle counting, so obviously process 2 actually is the farthest. So that's why for now, process 2 needs to go out, and the space that is being deallocated by process 2 can now be used by process 4. Okay, again, when a new process comes in, a new page fault will be generated. Now, next one after that, of course, process 5, because it's already there. Okay, process 5 remain there. And then process 3, okay, process 3 is allocated inside the frame, so nothing changes. Now, after that, process 2 actually comes in again. So, which slot will be given to process 2? Alright, again, we need to see here, okay. So, by coincidence, of course, process 4 actually finishes. Okay, hence, process 2 can use the space that was previously being used by process 4. So now 2 is here, 3 remain there, and 5 remain there. And then a new page fault is generated because process 2 now comes in. And then after that, continue with process 2, process 5. Okay, because process 5 is already there, so nothing changes. Next, process 2 again, because process 2 is already there, nothing changes. So the decision here that you need to remember for optimal policy, it will actually see which process actually needs to execute the nearest, and the one that is farthest in the order will be swapped out. Okay, that is how the decision is being made. Okay, if you need further understanding, please repeat again my explanation, and please ask if you still don't understand regarding this optimal policy. Now, for the next method, it is the least recently used method. So the key factor for this method is to actually replace the page that has not been referenced for the longest of time. So basically in this method, you need, or the OS need to actually tag which process has not been referenced previously to decide whether that process needs to get out or stays in the frame. So in this example, if you can see, Okay, so we have this process 2, 3, 1, and 4, and also 5. So in this case, again, we have 3 frames, and then these are the order of the process that will be coming in. So again, OS needs to actually have this information before decided which process to actually swap in or swap out next from the frames. Okay, so for the first one, we have 3 available slots. Alright, for the first order, number 2 came in. So of course, we have the available frame. Okay, number 2 can actually use this free slot. And then process 3 comes in. Alright, now it can also use the second slot. And then process 2 again will return to execute. So because number 2 already there in the slot, there will be no changes in the allocation of slots. Next, we have process 1. So because we have one available slot free, so now process 1 can actually use the slot. Now, the decision factor is after another process comes in. So this time, 5 comes in. So the OS needs to decide which process need to actually go out from the selected frame. Now, the decision here is to decide or based on the factor that the process which has the least recently referenced in the previous allocation. So in this case, okay, if you see here, okay, for process 1, you have one reference, but there is a very new process that comes in. And then for process 2, we have two reference previously. We have here, and we also have here. So it has two reference. Next, process 3. So based on previous allocation, it has only one reference. So based on this factor, process 3 need to give way to the new process, which is process 5. So process 5 will take the spot from process 3. So process 3 needs to be swapped out. And then the next order, we have process 2 comes in again. So no changes here because process 2 is already in the frame. Next comes process 4. Okay, for this one, okay, actually process 1 actually finishes. So there will be no process 1 in the future. So because of that, process 4 will use the slot being left by process 1. And then after that, process 5 execute again. So nothing changes because 5 is already in the slot. And then the next decision, process 3 is returning again. Alright, so this one, it needs to decide which process needs to actually go out to give way to process 3. Again, based on the decision, okay, we look at number 5. So number 5 previously, before the previous allocation, we have two reference, one here and one here. So there will be two reference, but before that, we have only one reference of process 2, which is there. So based on this factor, process 2 needs to give way to process 3. So process 3 will take the spot from process 2, hence we get 3, 5, and 4. And then the process continue. Okay, so after that we need process 2. Again, based on the factor, we see the one that is the least one is process 4. Hence, process 2 will take the spot of process 4. And then after that, 5 and 2, because 5 and 2 is already there. So 5 and 2 will stay in the slot. So this one continue, and it will always look at which process has the least reference before deciding which process needs to actually make way for the new process. So that is the key factor for least recently used algorithm. So for the third one, it is the first in, first out algorithm. So simply put, this algorithm checks which process is has actually been the longest inside the frame. So for example, we see here, okay, still the same order of process coming in: 2, 3, 2, 1, 5, 2, 4, 5, 3, 2, 5, 2. These are the process that will be coming in and out. Now, we have 3 slots. So for the first round, of course, we have 3 available slots in the frame of memory. So 2 will occupy for the first order, and then third one, here it will use the second slot, and then process 2 again. Nothing changes because 2 has already been allocated a slot in the frame, and then process 1 comes in. So we have still 1 available slot. So 2, 3, 1 each are given the memory frame slot. Now, when process 5 comes in, it needs to check which process has been the longest in the slot. So from the diagram here, we'll see that, okay, we have 4 cycles of process 2 previously has been allocated a spot inside the memory, while process 1 only 1 cycle, of course, because it's just arrived before, so only 1 cycle for process 1 before. And then for process 2, we have 4 cycles of process 2. So based on this scenario, we see we have 4 slots or 4 cycles of process 2. We have 3 cycles of process 3, and we have only 1 cycle of process 1. So for that, process 2 needs to be swapped out. Process 5 comes in and use the previous slot allocated to process 2. So now we have 5, 3, and 1. And a 1 page fault is generated once a page change is happening. So 5, 3, 1. Now after that, okay, after just 1 cycle, process 2 is returning again. So again, the same check must be made. So in this case, we have 2 cycles for process 1, 1 and 2. We have 1 cycle for process 5, okay, here. And then we have 4 cycle of process 3. See here, 1, 2, 3, 4. So based on this decision or this scenario that has been checked out, so process 3 need to go out and give the slot to process 2. So now we have 5, 2 and 1 in the memory frame. Alright, so after that, process 4 comes in. Again, the same comparison need to be made. Which process has been the longest? So based on the information, process 5 only 2 cycle. Process 2 only 1 cycle because it just recently entered. And then for process 1, we see 3 cycles of process 1. So based on that, process 1 needs to go out. Process 4 comes in. Now, after that, process 5 execute again. So nothing changes because it's already in the memory frame. And then process 3 is returning to execute. So we check again. So there are 3 cycles of process 2. Okay, 1, 2, 3. We have 4 cycles. For process 4, we have 2 cycles, 1 and 2. For process 5, we have 4 cycles. Okay, 1, 2, 3, 4. So based on that information, process 5 need to go out and give the slot to process 3. Now we have 3, 2, and 4. After that, process 2 is executing. Nothing changes because 2 is already there. Now, after that, process 5 is returning again to execute. So which process needs to go out? So based on the information we see, for process 4, we already have 4 cycle. For process 3, we have only 2 cycle. For process 2, we have 5 cycle. So based on that comparison, 2 needs to go out. So the slot need to be given to process 5. And then after that, 2 is returning again. So based on the comparison again, we see 4 is the longest cycle. So 352 is the latest of process allocation in the memory frame. Alright, you can try to repeat again what I've explained now and try to understand what is the difference between all these three algorithms. Before we continue to the next part, please review whatever we have covered previously, particularly on the concept of the replacement algorithm involving the first in, first out, the least result use, and the optimal method. So once you have already reviewed those concepts, you may continue for the next part, which is on disk cache. Previously, we had covered the concept of buffering between I/O devices and transmitting the data from these I/O devices to the main memory or perhaps to the disk. So the disk cache holds the same concept. It's just that it has the buffer inside the main memory. It holds some of the partition of data that it needs to be transported while the transportation happens. So basically, the disk cache is a buffer in the main memory for the disk sector. It contains some of the information needed for transportation or when you are actually copying and moving around data in between location from the I/O device to the main memory. So inside the main memory, we also have these memory buffers to help during the transportation of data. Usually, this cache is being used for faster transportation between the I/O device and also from the memory sector that is needed. So for example, let's say you want to print a certain data or want to read certain data for that particular I/O device. So for example, it will ask this question. So is the data needed inside the memory cache or not? If the answer is yes, okay, the request is satisfied via the cache. If there is no related data inside the cache, then the requested sector is read into the disk cache from the disk. So basically, the information needed will be sent from the disk into the cache and then sent to the requested I/O device. So this is how this cache works because this cache memory is much more faster compared to loading from the memory itself. Remember from the previous example, we use buffer because buffer transportation of data is much more faster than what we have from the actual disk or I/O devices. So upon answering that question, when a new sector is brought into the disk cache, one of the existing blocks must be replaced. So obviously, this memory cache will be filled and full over time. So which block will actually need to go out is decided by this factor. We have the least recently used based on access time, and we also have the least frequently used based on the number of access. So for the least recently used, it will check whether the block has been in the cache the longest with no reference, then it will be replaced. Okay, if you remember the previous concept on memory replacement, the concept is also true here. So the most recently referenced block is on the top of the stack and is decided if it is previously was referenced, then it will go on top of the stack, and the ones that is perhaps not referenced the longest, it will go down and being stacked to the bottom of the stack. So for example, in the memory cache, so block A, the time used is just now. For block B, the time used is this morning. For block C, perhaps the time used is yesterday. So based on that decision, block C will be needed to go out and perhaps process for block D will come in and occupy the memory cache. For the least frequently used for the memory block, the block that has experienced the fewest reference, meaning it has not been used for the longest, will be swapped out and replaced by the new block of memory of data. So basically, each time a memory is being referenced, a memory cache is being referenced, a counter will accumulate to actually reference how many times does that block is being used inside the memory cache. So for example, for block A, it is being accessed 137 times, for example. Process B, block B accessed 57 times. For block C, perhaps the time access is only 10. So based on that comparison, perhaps block C can be replaced and the new block can be occupying that memory cache location. So this is, we have a counter. We see whether which block has been referenced the most, and the block that has the least reference will need to give way to the new block that will be using the cache memory block. For this part, we are going to look at RAID. RAID is basically some of the way to have backups of data after we have finished processing it or using it. Usually, for example, normally we have used the use of thumb drive perhaps, or the use of cloud storage to have a backup for our data. RAID is basically used at an enterprise level where you have a bulk of data that needs to be backed up because that data is a very important asset and we cannot afford just to store it on the cloud or perhaps on just a simple thumb drive. So RAID has a solution to have a proper backup for our critical data. So RAID is actually an acronym for the Redundant Array of Independent Disks. So it is actually a hardware and also both a method where data can be backed up, and there are many ways for the data that can be backed up on the RAID architecture. So depending on your organization budget, there will be 7 levels of RAID that can be used from 0 until 6. So this is based on how much backup that you need or how sophisticated is the backup that you need for actually restoring your data if something actually happened to the original information. In terms of the RAID method, the number for the RAID level does not actually signify the succession or the hierarchy of the RAID method. It simply put that which RAID level are you actually employing for your organization. First and foremost, these are the 3 characteristics for the RAID architecture. First of all, RAID is actually a physical disk drive that you have stored somewhere safe, perhaps in a remote location, and each time a backup is being made, there are a redundant disks that have parity of information. Let's say this 1, this 2, this 3, this 4, and so on. So each time a backup is being made, the information is spread across this 1, this 2, this 3, and this 4. So each of these 1, 2, 3, 4 of physical disks, it has the information from your organization location. So when you save a drive of information, it will be distributed to drive 1, 2, 3, and 4 based on which RAID level are you actually employing. So basically the data are distributed across the physical drive of an array in a scheme known as striping. So in the next part, we are going to look at how is this done in the RAID method. So for example purpose, we are going to look at just RAID level 0 and RAID level 6. So for RAID level 0, okay, the method here is one that is cheapest to implement and offers no fault tolerance. Basically, you just have this for this location, for example, and each of your data information is distributed, okay, upon this for location. So for example, when you're actually writing it, A, B, C, D will be distributed to 4 separate locations. And this is considered not a true RAID because it does not include redundancy. to improve performance and provide data protection. Basically, you just distribute your data across 4 locations, okay? But let's say something happened or someone actually messed with the information, you cannot actually effectively restore back that information. Okay. For RAID level 6, okay, instead of just having the striping of information across disks, now you have the parity information. It means that each separate location will have a parity information also installed there. So let's say for this first disk, it is paired with perhaps the disk, second disk, and then this second disk is paired with the third disk, this third disk is paired with the fourth disk, and so on. So this provide high data availability because you have the parity information. So in case anything happens, so you have information which you know that distribution of this, where is it going to, which disk do you have actually have the backup. So let's say this is your logical disk, means that you see your storage as one information or one storage space, but actually in real life those storage are being distributed into multiple location. So this is actually how cloud storage work. You actually store this information upon multiple servers that the service provider is actually giving you. You don't have actually one space inside one location, but your data is actually distributed among multiple locations on the service provider side. So basically for RAID, this is just an introductory level of perhaps what we can have for a safe storage for your backup of data. If you need further information on RAID, perhaps you can take the storage technology subject, which will cover thoroughly the method that's being used to safely store your data. So before we end today's chapter, let us review what we have covered in this chapter. First, we look at the concept of DMA and design objective of the I/O management. We also look at the I/O organization inside the system, where we have the hardware, the user, and also the system, in order for you to safely communicate and transferring data between the hardware and also the user request. We also look at the concept of buffering and disk scheduling, and also the concept of virtual memory replacement, followed by the disk cache, and also lastly the rate of storage distribution. So I hope you can try to review back what we have covered for today, especially on the use of buffering and also disk scheduling and the virtual memory replacement method. Okay, please try to do again what we have covered here. I will give you some exercise to further improve your understanding on the topic. And if you need my help, again, don't worry, you can message me or ask me directly during the discussion session. So I hope you have benefit from what we have covered today, and I will see you again in our next session. Thank you for joining.